This is a tutorial on how to perform regression statistics, particularly with Python. So what we're going to be doing with this tutorial is we have this data, you can see from the blue points there, about 99 data points, and we want to be able to predict a linear regression. Okay, so this line right here with a slope A and an intercept B, and that is going to be this one right here. Okay, so there's our expected correlation there, y equals ax plus b, and then what we have is a confidence interval around that. So this orange line right there, you can see that this one defines the confidence region where we expect the line to be, 95% confidence interval, and then we also have something called a prediction band as well. So prediction band is defined by these dashed lines, and that is if we took another data point, we would expect the data point to lie within that prediction band. So we can see here out of the 95 we have 1, 2, 3, 4, 5. So that's about right. We have 5 points out of the 99 that are outside that prediction band, and so we that's our 95% confidence that something in the future, if we take another measurement, it's going to be within in that region. Now you can also see that the errors are not normally distributed here. It looks like it might actually be something like an exponential function there. So we're going to cover that in the second part of it, is to fit it to a nonlinear correlation. Okay, and do some nonlinear statistics, linear statistics applied to this nonlinear regression. And we're going to do the confidence region right there, the confidence interval, and then also our prediction band. Okay, and you can see that the confidence region is going to widen out in areas that not close to where the data is. We're going to be less confident in those regions, obviously. Okay, let's go through the Python on how to actually do this. I'm going to go ahead and just let this type for me. Okay, I'll do it off here to the side, then as we're going through this I'll explain it just a little bit more. And let me just make this statistics.py. Okay, so I need the uncertainties package as part of this. If you don't have uncertainties, you may need to do a pip install of it. Just go to your command line and, for example, I'm going to open up a new command line here. Okay, command prompt, and you can do pip install uncertainties. Okay, and that'll make sure you have it installed. Okay, we need a couple other packages also, like pandas. You can also do pip install from your script as well. So if you don't have uncertainties, you can just include this next block that's there. You can try to import uncertainties, and if you don't have it, then you can import pip instead. So instead of doing it from the command line, you can do it right from your Python script, and then you can do pip.main and install uncertainties. So that'll also take care of installing it if you don't have it. Okay, so uncertainties is not kind of a default package. It comes with the distributions, but we're going to import it as UNP. Okay, uncertainty numpy. Okay, uncertainties package. Okay, and then I've got a data file here. This one is going to be, if I also select this link here, you can get to that. I'll just show it to you as this thing keeps going. We're just going to import that with pandas read CSV. We can just give it a URL data source, and it'll download it and parse the data. Okay, so there's the data file right there that we're importing right now. And then we're just going to parse out the values x and y, and then we'll also get our length of y values. We have 99 values that we're going to be importing. Next, we need to find our function, and this is going to be our correlation that we're going to use. You can put any correlation in there. It can be linear or nonlinear. In this case, I just have a slope and an intercept, slope being A and the intercept being B. And then I'm going to use curve fit, and it's going to return the optimal parameters, A and B, p-opt, and then the covariance matrix, a 2x2 matrix of the covariance, and I'll just retrieve those values from p-opt. Okay, and then I'll print the values as a next step just to make sure we get, this is our minimum that we need just to be able to do the regression. Okay, just be able to get A and B values. Okay, and then what we're going to do is we're going to compute the R squared value. Okay, so just a standard R squared value here. If it's closer to 1, it means it's a better fit. If it's closer to 0, it means there's no, the variance in y is not explained by the variance in x. But if it's closer to 1, then it just means that the variance in y is explained by the variance in x. Okay, now we're going to calculate the parameter confidence interval. We'll do this with our UNC package, the uncertainties package, and then what we need to do, we'll get our A and B values, and this will print not only the value of A, but it'll be A plus or minus a certain value. So it'll give us our confidence interval on the parameter itself. Next, we want to plot our data, and then we're going to, so this is the first thing that we'll do. Just label it data, and then the next thing that we're going to do is we're going to calculate our regression confidence interval. Okay, and so this is our confidence interval, the confidence region where we expect our linear values to be within that region. So I'm going to sample just points between 14 and 24, 100 points, and we will calculate py. Okay, this is px is just going to be a vector of 100 values, and then py is going to be our a times px plus b. It's going to include those uncertainty quantities as well. And then we need to get the nominal value for our correlation, which is nom, and then standard deviation, which is our standard deviations as well. We'll use those to be able to plot the uncertainty region. Okay, so what we're doing right now is doing the prediction band. Okay, so we don't have a standard package that'll do that for us, so we're just going to program that ourselves. The last part that you saw there from the nominal, okay, this is our nominal right here, and then we're going to use that standard deviation, the plus or minus 1.96 times our standard deviation, and that's going to give us our confidence band right there. Okay, this is our prediction band, very similar, but we're going to use our alpha. Okay, and that's going to be 0.05, so 95% confidence. And then we have our number of points, our number of samples. Okay, one of the things that you'll notice with with these is that as the number of samples increases, this this confidence interval right here is going to shrink, and it's going to get very precise. Okay, but as the number of samples increases, we're still going to have the noise, and this one is not going to change very much. The prediction band is not going to change. It's going to kind of stabilize to a certain band. It's going to include about 95% of the data points. Okay, so that's just a difference that you'll see is more data points will narrow the confidence region or the confidence interval, but the prediction band, it will stay at whatever the the noise or the variance of the measurements. Okay, and then we're going to get we're going to use the student t there, the quantity with our given number of samples and number of parameters. Okay, and the alpha value that we requested. And then here's just some calculations. Let me just show you these equations because they're a little bit hard to visualize. So here are the equations. The ones that we're going through right now are the prediction band. Okay, and we're trying to answer the question, where will y naught be found if we're measured at x naught? And that is the formula right there for the prediction band. Okay, this is the one that we're going through right now. And you can see the confidence interval one. This is the one that was taken care of by the uncertainties package. given a specific value for x and x naught, what is the error in y hat naught? Okay, and so we're going to be using, we use this one right here, and that was already computed in the uncertainties package for us. Okay, where this is sy right there. It looks kind of complicated, but it's actually not too bad. Okay, and so we're just continuing on with this one. You can see the predicted values, the best fit model. We see now we're calculating our prediction band. Okay, there's our prediction band, and that's going to be our dy, plus or minus dy, and then we'll return a lower and upper prediction band. So we're doing the plus or minus right here, and so here's our lower prediction band and then upper prediction band, and then we're going to have yp minus dy and then yp plus dy. Okay, and then we'll just return those two, and those will be our upper and lower that we'll then plot. So let's go ahead and just call that function with our prediction band. We have px. Okay, px are the 14 to 24 100 points, x and y, and then we have our optimal parameter values and our function name. Okay, f, and then here's our plot the regression. We're going to plot the nominal values. So this is the one that we're plotting the black line right in the middle. Okay, that's this one. That's our plotted the data already. This is our regression curve. Now we're going to plot the orange lines. These are going to be the uncertainties. And we're going to do nominal minus 1.96 times the standard deviation. I'll put that as orange. I'll give this one a label. Okay, so I'm just going to add this label right here with the 95% confidence region. Okay, and then I'll do the same for the upper, but I just won't give it a label, so I don't put two labels in my plot. Okay, there's now the prediction band. Okay, we already got the prediction band, and so this one's pretty easy to plot. Okay, I'll just do px times with the lower prediction band on the y-axis, and I'll give that a label. Okay, just added that label right here. There's our prediction band. I'll do that for the upper and the lower. Okay, give it a y label, give it an x label, and then add the legend, put it in the best location. Now I want to just save the plot, save it as a PNG file, and I'll show the figure. So if you just do plt.savefig, you have regression.png, and we'll show it. Okay, so that's it. Let's go ahead and run it now. I'll go ahead and save this one. And one thing, okay, I'll do edit with IDLE. One of the things you might want to do here is if it didn't have uncertainties, this one's going to fail right there. Just go ahead and put this down here, in here. So if it can't import this one, you probably don't have the uncertainties package. Once you install it, you can put both of those in. Okay, so I'll go ahead and run it, and let's see if we get this plot. Okay, it says UNC is not defined. Okay, I need to do that in here too. Okay, let me put that, because I do have it installed. There we go. Okay, I'll go ahead and run it, and there is our confidence region and our prediction band with our data. Okay, now you can also see a couple of things at output. We had the A and the B values, as well as the R squared value, and then the uncertainty. So we have A is going to be 0.0361 plus or minus 0.0035. And then B, the intercept, is negative 0.57 plus or minus 0.07. So there's our confidence on the intercept. Okay, now we're going to go on to the next part of this, and let's say we just had a nonlinear correlation that we wanted to fit this to. And this one is going to be, instead of y equals ax plus b, we're going to change that, and we're going to try to fit this to a, and then we have our exponential. Okay, and fit those three parameters instead. So part of this will just be, modifying it so that we add another parameter, but also do a nonlinear correlation instead. So the very first thing we need to do is come down here and just change this to a times, I'll do numpy.exp, and then do b times x, and then plus c. So there's our correlation that we're going to be fitting. And I'll add my c parameter right there. Okay, now I'll add another output here. There's a more efficient way I could do that on one line if I wanted to. I'll just write it out as another line. Okay, and there's C and C. Okay, so I'm just going to print those. The r squared one stays the same. And here I have another one that comes out of this one, another parameter. And let's print that uncertainty as well, just so we can see the 95% confidence interval on that. Okay, and there's my scatter data. That one's going to stay the same. I'm going to change this correlation right here. And this one, I need to change this to, it's going to be uncertainty numpy.exp. I can't use np.exp. I need to use the package for uncertainties, uncertainties.unumpy, uncertainty numpy as ump. Okay, so I need to use that one instead, just so it can propagate the plus or the minus there. And it'll be b times x plus c. Okay, and I think the prediction band should stay the same, that function there. And let's see if I've got anything else here. I'll just go ahead and change this one, a times exp to the b times x plus c. Okay, and then let's see if there's anything else that we need to change. So just changing this to fit a nonlinear correlation and do the statistics on that as well. I'll just try to run it and see if we get an error somewhere. Okay, so it's missing one positional argument there. I guess the r squared did need to change because we had that function in there for our r squared value. Okay, and I'll go ahead and run it one more time. Okay, another error here. Let's see. Oh yes, I know what that is. It's on line 86, and it looks like our px and nominal, those are different dimensions. One is 100 in length and one is 99. So I think I just need to come back up here. I made a mistake right here on, let's see if I can find it. Okay, so I needed, instead of x there, I need to use px because I needed those 100 different values, not the 99 from the data. Okay, and that will give us our py for the confidence interval. So we specify the x's there. We don't use the ones that were from the data. Okay, let's run that again, and there's our fit right there to the a times exp bx plus c. Now let's just look and see what those came out to be. There we have our a, b, and c value. There's our r squared value, so a little bit better than a linear regression. And then we had our uncertainty right there. It's that kind of printed out a little bit weird. Plus or minus 2 plus or minus 5e to the minus 6. Okay, and then 0.53 plus or minus 0.11, and then 0.043 plus or minus 0.018. So nonlinear, or the confidence interval for this says that It looks like that does not include 0 for that C value. So it looks like it's above 0. We can't necessarily get rid of that C parameter, it says. Okay, so we have our confidence region, our confidence interval, our prediction band, and our nominal regression there for the nonlinear case with 3 parameters. Okay, so that concludes this tutorial with Python. Again, I'll just point you at this page right here. Give a little bit more information. It'll give the give the source code for this. And then if you're going to use this source code, I recommend using the get code right down there. Just go ahead and select that. It'll give it to you as unformatted text, so you can copy and paste that. And then we'll also, here's the nonlinear regression. I'll put the source code there as well for this one. And then I'll do some more with joint confidence regions. And a little bit, we're using linear statistical analysis there. And there's some interesting things that happen with a nonlinear statistical analysis on the parameters. So I'll post some additional content there. I don't have it quite developed yet, but it should be there by the time you're checking it.